In this video, we're going over the concepts for Chapter 6, which is titled Gases and Solutions. Let's understand that there's many molecules at room temperature that are found as gas forms. Typically, molecules with fewer than 5 atoms from the first 2 periods in the periodic table are gases at room temperature. As we can see in the image on the right side of the slide, we have some gases that are elements, including hydrogen, nitrogen, oxygen, fluorine, and chlorine. Those are homoatomic elements, and we can see that we call them diatomic molecules. Next, oxides of the nonmetals from the upper right corner of the periodic table tend to be gases at room temperature. Those include carbon monoxide, carbon dioxide, nitrogen monoxide, nitrogen dioxide, sulfur dioxide, and sulfur trioxide. Lastly, let's understand that we have a whole group within the periodic table that are found in gas form, and that is group 8A in the periodic table, and that's where we have the noble gases. Additionally, in the image that we have in the right side of the slide, we can see other pure and mixed gases, at least propane, if from organic origin, and we have some toxic gases, including ammonia. In order to understand the behavior of gases, we need to go over the kinetic molecular theory. This theory explains what a gas consists of and some of its behaviors. Let's establish that a gas is going to be one of the states of matter, and it consists of small particles. One of the things about the theory is that when it comes to these particles, they're going to move rapidly, randomly, but it's going to be in straight lines. These particles have essentially no attractive or repulsive forces, so they are going to move freely. The particles are also very far apart. So that means that gases can be compressed, but also can be expanded. When it comes to the volumes of these particles, they have small volumes when we compare them to the volume of the container they occupy. And because these particles are going to be moving, their kinetic energy is going to increase when we increase the temperature. In the right side of the slide, we have a container containing gas particles, and we can actually see how these particles are going to be moving in straight lines when they collide with each other, or I should say, until they collide with each other or the walls of the container. Gases are described in terms of 4 properties. In table 6.1, we have the 4 properties of gases. The first one is pressure. Pressure is defined as the force a gas exerts on the wall of its container. There are many units that can be utilized in order to measure pressure, and they are listed in the last column of the table. Next, a gas can be described based on its volume, and volume is going to be the space that a gas occupies. Additionally, there are some units of measurements that can be utilized for volume. Next is the amount of gas particles, and those are going to be measured in moles. Even if a measurement is given in grams, moles is the unit that it is utilized in equations. Lastly, temperature is a property of gas that specifically measures the kinetic energy and rate of motion of gas particles. It can be measured in Celsius or it can be measured in Kelvin, But if the measurement for the temperature of a gas is given in Celsius and a calculation needs to be performed, Kelvin is the one that is utilized for calculations. So if Celsius is given, it needs to be converted to Kelvin in order to do a calculation for gas properties. Now we are going to focus to talk about particularly about pressure. When pressure is measured, a barometer is the instrument that it is utilized to measure the pressure exerted by gases in the atmosphere. A barometer is going to indicate the atmospheric pressure as the height in millimeters of mercury that are present in a column. Now, when it comes to barometers, they were the barometer was invented by Evangelista Torricelli. And you can see an image of the scientist on the right side of the slide. The barometer that he created specifically had a column, as we can see here, that had mercury. And in this column that specifically has a vacuum, the premises of this barometer is that overall, when the atmospheric pressure specifically acts on the pool of mercury, then that is going to make the millimeters of mercury fluctuate. So because of his studies is how we know that atmospheric pressure is going to be varied on location. Since then, because we know the toxicity of mercury, barometers have also been made in digital form, as we can see in the bottom right corner of the slide. There's going to be some conversion factors that we need to be familiar with. And for example, if we have the measurement of 760 millimeters of mercury, that is going to equal 1 atm or 1 atmosphere, which is one of the units for pressure. Also, millimeters of mercury is a unit for pressure. Additionally, 1 atmosphere also equals 760 torr, which is another unit for pressure. As you can observe, there's going to be conversion factors that can be utilized in order to convert from one unit to the next when it comes to pressure. Now, let's explore the whole idea of atmospheric pressure, which is something that was discovered by the barometer developed by Torricelli. Atmospheric pressure specifically is the pressure that is exerted by a column of air from the top of the atmosphere to the surface of Earth. One of the things that Torricelli was able to prove with his barometer is that this atmospheric pressure is going to vary depending on location. It is known that the trend is that atmospheric pressure decreases as altitude increases. As you can see in the image on the right side, we can see that at high altitude, there is less pressure felt by a person, while at sea level, the pressure is known to be at least 1 atmosphere or ATM, which is a unit for pressure. One of the important things when it comes to pressure exerted by a gas is that we know how to do conversions. Let's do a practice problem converting units of pressure into each other. As you can see in the practice problem, it reads, hyperbaric therapy uses oxygen gas to help heal wounds. The gauge on the cylinder of compressed oxygen gas reads 1500 decimal place PSI. We are going to express this pressure in units of ATM, torr, and millimeters of mercury. We can see that specifically in the table that we have in the bottom right corner, we have the different equalities that can be utilized in order to change these units of measurement into each other. So let's first do the conversion between PSI to ATM. We write the measurement given, which is 1500 decimal place PSI. In order to do this conversion between PSI and ATM, I'm going to highlight the conversion factor. Since we're going from ATM to PSI, we can actually observe that 14.7 PSI equals 1 ATM. Utilizing dimensional analysis, we are going to place the 14.7 PSI in the bottom, and on the top, we're going to write the unit of 1 ATM or 1 atmosphere. When we take these values and we put them in the calculator, 1500 divided by 14.7, we see a calculator display that shows a value of 102.04, and there's many digits. Since our given unit has 4 sig figs, we're going to round our answer to 4 significant figures, which means that our final answer is 102.0 ATM. Next conversion that we have is PSI to torr. We're going to write the measurement given. When we are looking specifically between PSI and torr, as you can see on the table, specifically, we are going to observe that we are going to use our value for PSI to ATM, and then we're going to include the ATM to torr conversion. So we're going to use 2 conversion factors. We're going to use the one that we use on letter A, 14.7 PSI, to 1 ATM, and then 1 ATM equals 760 torr. In order to do this conversion, I'm going to take 1500, multiply it by 1, multiply it by 760, and then I'm going to divide that by 14.7. Based on my calculator display, I'm going to round this in scientific notation to the 4 sig figs needed, which is going to be 7.755 times 10 to the power 4 torr as our unit. Understand that you can actually use the regular notation number, which is going to be 77,550. I decided to put it in scientific notation. Lastly, we need to change from PSI all the way to millimeters of mercury. One of the things that we can observe is that torr and millimeters of mercury are equivalent to one another. 760 millimeters of mercury equals 760 torr. So the relationship between millimeters of mercury and torr is 1 to 1. So that means that the conversion for letter C means that since we already found in example B what is the measurement in torr, that is also going to be equivalent to millimeters of mercury. So the answer for letter C is also 7.755 times 10 to the 4, but now the units are going to be millimeters of mercury. The behavior of gases can be explained through mathematical relationship. These are known as gas laws. By definition, a gas law is going to be a mathematical relationship that describes how gases behave when their pressure, volume, temperature, or amount changes. These gas laws are going to be based on experimental observations and the kinetic molecular theory. Even though there's many gas laws, in this class, we're only going to explore a few, starting with Boyle's law. Boyle's law is going to be the gas law that is going to describe the relationship between pressure and volume. This relationship for pressure and volume is only going to be true if the temperature of the gas is held constant and also the number of moles. Boyle's law is given by the following equation. Initial pressure times initial volume equals final pressure times final volume. The relationship between pressure and volume is inverse proportional. The way that we write this is in the following equation. Pressure, this is the symbol for proportional. And since this is an inverse relationship, we're going to put 1 over V. What this means essentially is that if we look at the relationship between pressure and volume, notice that I'm actually putting 3 lines because this is just relationally relating pressure and volume. Since they are going to be inverse proportional, when pressure goes up, therefore, volume is going to go down. If pressure goes down, then what happens is that volume goes up. And that's what it means to be inverse proportional, meaning that they're going to be going in terms of trends in opposite directions. One of the main applications for Boyle's law is represented in how the human body actually intakes air in breathing. Also, during the process of exhalation, we can see Boyle's law at work. Let's explore it by looking specifically at the diagram in figure 6.5. When the human body inhales air, what happens overall is that the volume of the chest cavity is going to increase. So that means that we're going to see an increase in the volume. Then, because the lungs are expanding, what overall they experience is going to be a reduction in the pressure that they feel because they need to expand. So the relationship of increasing in volume but lowering the pressure in the lungs is what we experience when we inhale air. When we exhale air, what happens overall is that the volume of the chest cavity is going to decrease, just like we see in this relationship. So that means that overall, for exhaling air out of the lungs, we're going to increase the pressure in the lungs. So then this is what's going to be causing the air to rush out in terms of going to be released in the atmosphere. So upon exhalation, this is the relationship, a reduction in the volume of air in the lungs, but an increase in the pressure that the lungs feel. The other gas law that we're going to be familiar with is going to be Charles' law. Charles' law is going to describe the relationship between the volume of a gas and temperature. Charles' law is only going to be true if the gas is actually at constant pressure and constant number of moles. When it comes to the relationship in Charles' law, we can see that the equation is right here on the slides, which basically says that initial volume divided by initial temperature equals final volume divided by final temperature. The relationship between volume and temperature is direct. So when we write the relationship, volume is proportional to temperature. So what this means is that when we relate volume and temperature, if temperature goes up, volume goes up. If temperature goes down, volume goes down. One of the best examples for looking at Charles' law is the idea of hot air balloons. In hot air balloons, we have a device that is going to be heating up those gas particles of air that we have in the atmosphere. As those gas particles are going to increase in temperature, then since they increase in temperature, we're going to have increase in volume. So that's why in a hot air balloon, we see inflation of the balloon itself, because now we have an increase in volume of the air, and that's why they work and they get lifted.